Well, thank you very much. It's a real pleasure to be here and to contribute to the panel on clean water initiatives and sustainability. So I'm a faculty member here at Nipissing University, here on this shared campus. And when Harriet contacted me this spring about this summit, I offered to speak about a recent study we've completed on assessing elemental budgets and the Lake Nipissing, assessing Lake Nipissing water and elemental budgets, specifically looking at total phosphorus and chloride budgets for the lake. This work has been just accepted into a peer-reviewed academic journal in the Journal of Great Lakes Research, and that was just a couple of weeks ago. It was co-authored by myself and Rebecca Schneider, who's working in my research group right now in the Department of Geography, as well as several colleagues at both Nipissing University and the Dorset Environmental Science Center, which is part of the Ministry of Environment, Conservation and Parks, and so they're listed here as contributors. In the second part of this title, I wanted to deliberately highlight the need for development of community-based monitoring of the lake and its inflows, and that the current lack of monitoring will impede, in the long term, our abilities to understand and manage the lake and its watershed over the long term in the context of stressors of land use and climate change. We can think about Lake Nipissing and its watershed in the context of the UN Sustainability Development Goals, which I'm still learning about, and it was a really great opening, I thought, to today's session from our first speaker. And so here I've highlighted goal 14, but it could also be, I guess, goal 15 of, was it life on land as well, that fresh water might fit under. In order for lake resources to successfully contribute to human well-being, ecosystem integrity, we need properly functioning biogeochemical and physical processes. These are required. And so if we get back to the title of our talk here, the anthropogenic sources of total phosphorus and chloride to lakes and rivers can have harmful impacts on lakes and other freshwater ecosystems. They've been pollutants of concern for many decades in the Great Lakes basins. And the study of contributions of total phosphorus and chloride in northern boreal shield headwater tributaries like the Sturgeon Lake Nipissing French River Basin, in which we all reside, are understudied components of the Great Lakes Basin. This is just a few examples, very recent examples within the last year, studies that offer examples related to assessing trends, in this case, of chloride concentrations here in Ontario and Lake Michigan. So assessing the study that we see here recently reported on for Ontario looks at chloride trends in Ontario's surface and groundwater. Over 2,500 surface and groundwater sampling locations, and they show that many lake, stream, and groundwater locations proximal to roadways and urbanized areas meet or exceed the chronic exposure guideline of 120 milligrams per liter in chloride concentration, and that these regional areas are persistently increasing in concentration. The evidence implicates road salting activities for winter safety as a primary contributor to elevated chloride. Certainly there are other sources related to agriculture, for instance, but in this particular study, that's kind of one of the aspects they highlight. The recent Lake Michigan study that we see also highlights another example showing increasing tributary loading of chloride to Lake Michigan, anticipating that chloride concentrations in the lake will likely continue to slowly rise in the coming decades. This study also is of interest because it emphasizes the enormous variation in chloride concentration and loads in their spatial assessment, the massive lake, and looking at all the tributaries coming into Lake Michigan. If we think about Lake Nipissing, of course, we're not at the scale of Lake Michigan, yet nonetheless it's quite a large system, and we'll kind of talk to that. Just another aspect here, this idea of elemental budgets, where we assess all the inputs and outputs of both water, as illustrated here with precipitation and evaporation, the inflows and the outflows, as well as groundwater exchange. So we assess all those inputs and outputs in water, as well as the elements like phosphorus and chloride. This elemental budget has been a foundational approach that we use, scientists and managers, to build our understanding of aquatic and terrestrial hydrology, their linkages and human impacts, and management potential we've been using that for a long time. So it speaks to that idea of assessing properly functioning biogeochemical and physical processes. While elemental budgets are often used then to help us understand water quality of a water body and to set targets for lowering inputs, they have yet to be calculated for Lake Nipissing. Like many of you already are highly aware of the challenges associated with phosphorus entering the streams from urban and agricultural sources and contributing to the eutrophication of surface water bodies and contributing to issues associated with harmful algae blooms, and that issue is in fact complex. While a total phosphorus budget has been performed for Canadore Bay on Lake Nipissing, nutrient targets do not currently exist. Evaluations based on macroinvertebrate sampling in 2000 categorized 8 of the 12 major river inflows to Lake Nipissing as either impaired in water or marginal in water quality designation. So the water quality of Lake Nipissing itself has been conducted, or surveys have been conducted and been assessed on a 10 to 15 year period, so in the late 80s, early 2000s, and then in 2015-17, at the same time that we were conducting our study that I'll speak to next. But generally speaking, there's limited data with which to evaluate change in concentrations, and a comprehensive elemental budget and water budget remains to be assessed. And so this was the basis or the context in which we set out to study or conduct a study on Lake Nipissing. The goal of the project then was to develop the first chloride and total phosphorus budgets for Lake Nipissing, to quantify all the annual and seasonal flows, as well as the current or the contemporary total phosphorus and chloride concentrations from tributaries, put them into the context of historical observations where they were available, and to estimate the annual loads, so how many tons per year, or yields, which would just be the same idea of mass but per unit area per year. As well as their spatial distribution in relation to land use. So this is the watershed. This would be the Sturgeon Lake Nipissing French system or basin. So that would take us all the way down to Georgian Bay. But the top part of it here would be, of course, the Sturgeon River component, which would capture water all the way up north of Lake Temagami, which we can see here in the top part of that image, and it would collect water through that entire area and flow into Lake Nipissing. And then we can see outlined in black smaller catchments that would generate water along the Viv River, for example, Mosquito Creek, here's Chippewa, the Wassee, the South River, right? So we see a wide range of these catchments. The watershed that provides water to the lake is around just shy of 12,000 square kilometers in size. And so here we can see the extent, we can see the outline of the subcatchments that are defined by the tributaries and surface topography that flow into the lake. And the color scheme here is showing us information on land cover. We are showing that because this has been shown to be associated with pollutant contributions to rivers and lakes. Overall, the land cover is predominantly forested. So 50 to 96% of these individual catchment areas are forested. But we do have catchments that include up to 50% urban, such as Chippewa Creek, as well as up to 20% agriculture by cover. And that agriculture includes both crop and livestock farming. So as part of this estimating the water budget for the lake, we assembled the data where we could as a first step. Estimating the water budget for the lake is important because estimating elemental loading of chloride and total phosphorus, these are dependent on the amount of water flowing in and out of the lake. So when we calculate pollutant loading, we take the stream flow in cubic meters per second, and we multiply it through by the concentration of these elements in the water to get the overall mass or loading to the lake. So if we look here at the supporting data that was available, we have weather information or precipitation, annual precipitation from Environment Canada weather station at the airport, for example. Of the 13 tributaries moving water into the lake, there exist 5 gauging stations, so that would be a combination of Water Survey of Canada stations, for example, that measure stream flow in real time and are publicly available. And then we also sought out information from Ontario Power Generation and West Nipissing Power Generation for stations on the Sturgeon and the South Rivers. That left 6 tributaries where we had to model stream flow, so weighting it based on the catchment area and existing information at other gauging stations with similar land use. We also included data from municipal wastewater reports, and there would be no direct information or that would allow us to independently estimate a net groundwater contribution to the lake. This would not be uncommon, and I'll speak to that a little bit in a slide to come. For water quality, or the actual concentrations of chloride and total phosphorus in tributary inflows, we actually physically went and surveyed the tributaries monthly. So from 2016 to 2018, we conducted monthly surveys, collecting water samples from 11 of the 13 tributaries for year 1, and then 7 of 13 during year 2. And this included collecting samples during the winter where conditions allowed. At the same time that this was going on, the Dorset Environmental Science Center colleagues there were conducting the most recent in-lake survey of concentrations during the ice-free season over the course of multiple summers. So that overlapped nicely with this effort. And all the data was analyzed through the Dorset Environmental Science Center in their laboratory in Dorset. So this is just a few things that have come out of this study. Here in these diagrams, we're looking at historical concentration data available for different tributaries or rivers that are available through the Provincial Water Quality Monitoring Network. And you can see here that there's only select sites where this data is available. It goes back into the early 70s or late 60s, but you can see that data turn off in the mid-90s, and then in some instances it's turned, or they've reinitialized monitoring, but in many instances they haven't. And the red symbols here just indicate where we did our sampling for this specific study for those 2 years. So generally, and here we're looking at concentrations of total phosphorus in micrograms per liter on the y-axis. So since the mid-1970s, generally, total phosphorus concentrations have decreased in these tributaries where we have data, except for in the case of the Lavaz River. The decreases are consistent with general trends observed across the province. But the current median and mean total phosphorus concentrations are observed to be above or close to the provincial water quality monitoring objective of 30 micrograms per liter. That's the dashed line we see here for 5 of the 11 tributaries. Of course, the Wassee is of particular interest because it flows into Calendar Bay, the municipal source of drinking water. Here's the same information, but for chloride, again, looking at these general information by decade. We note for comparison, there's two dashed lines on these figures. The top one, for comparison, is the 120 milligram per liter level. This is the Canadian Water Quality Guideline for long-term exposure for the protection of aquatic life. But we also note the 50 milligram per liter threshold here as an important physiological threshold for aquatic biota. So chloride concentrations show increases since the 1970s for all sites. For some of these sites, that's really a small change of 1 to 2 milligrams per liter. So we can see very little change in Sturgeon Falls in the top left, for example, or the Sturgeon River. While other sites show large changes, greater than 20 milligrams per liter, for instance, in the Lavaz and the Chippewa Creek examples. We've generated water budgets for 3 water years, so from October through September. And here we expect that on an annual basis, we can independently estimate all the inputs of the water. So here, that would be the positive numbers, where we see the blue, the dark blue, which is all the stream flow that is gauged and being monitored or are being measured. The ungauged inflow in the green would be precipitation, for example. Those would be all inputs to the lake. And that they should, we can independently estimate those, and they should balance by all the losses or independently assessed losses of water from the lake, including evaporation and the big orange bar, which would be the outflow through the French River, as well as any change in storage in the lake over the year. Our water budget is pretty good because it compares favorably to other studies of large lake systems. Our inputs are within 9 to 14% of the outputs, so we're consistently missing about 9 to 14% of water as inputs, and we expect that this is a result of either a net groundwater input or contribution of area not included or represented by the tributaries. These results and their uncertainties is on par with other studies, as I've mentioned. And here I wanted to show just briefly some results of the elemental yields. So this goes back to that mass of chloride or total phosphorus per unit area per year that is being generated by the different catchments, the different tributaries. And so we've estimated how much mass of chloride and total phosphorus are being generated per unit area for each catchment. This is our definition of yield. And here we show this for each catchment. And so in the bar chart, we see here the dark shaded bars is total phosphorus, and the light bars are chloride. So I'm just going to go over this very generally, so I know there's a lot of information there. Generally, what we see is that some catchments are disproportionate sources of chloride and total phosphorus to the lake. So they punch above their weight in how much mass of chloride and total phosphorus that they generate per unit based on their area. For total phosphorus, catchments with these higher yields generally appear to correspond with the higher impacted land use. So higher total phosphorus yields for the top yielding 5 catchments account for 15% of the annual inflow to the, of rivers or from rivers to the lake, but 37% of the total phosphorus loading from rivers, with a single catchment, the Veuve, accounting for 24%. If we turn to chloride, chloride is more variable with a less obvious association with the percent impacted area. The highest yield is estimated for Chippewa Creek, for example, with other catchments with mixed land use ranging from 8 to 20%. So the top 4 catchments generating chloride represent 3% of total inflow of water to the lake, so a really much smaller amount, but 18% of the overall chloride loading that we've estimated. So again, just examples of punching above your weight per unit area. So some of the takeaways from this study, the big limitations, some of the things I learned when we attempted this was there are big limitations in the current monitoring that challenge a watershed scale approach to assessing elemental budgets. Water quality monitoring of Lake Nipissing inflows, all those tributaries, have generally been absent from provincial monitoring since the mid-1990s, with only 3 tributaries on the eastern end of the lake only recently reactivated. So there's 4 tributaries being monitored for water chemistry. And this presents a big challenge in generating elemental budgets and as a result, using it to think about and plan long-term watershed management. The current monitoring challenges are ability to implement then this type of assessment. And we've got examples then of catchments that, while gauged, may not be monitored for stream flow and yet represent an important component, or at least as we estimate it, an important component of loading. While the water budget is close to balance in terms of our calculations matching up the inputs and the outputs, the results suggest a groundwater or additional catchment contribution, and that's interesting from understanding the system kind of point of view. It could also be important for long-term elemental budgets. So here we see examples in the literature, for example, where they monitor and watch or have documented the development of groundwater accruing buildup of chloride over long periods of time, for example. And if we have a groundwater net inflow to the lake, then that could obviously influence our budget. The total phosphorus budget, despite the coarse sampling, the tributary loadings that we've calculated compare well with more detailed estimates from, say, the Wassee River, where we've done more detailed work. We can also compare those estimates to other studies, so we can see the loadings are similar to undisturbed forest watersheds, like in the Muskokas in some instances. And then for other catchments, they look a lot like the mixed land use boreal shields watersheds from Finland, where they've done similar types of studies. The budget doesn't close for phosphorus, and this indicates the lake retention, so consistent with sedimentation and other in-lake processes. And the phosphorus cycle is really quite complex, and there's many unknowns here. There's uncertainties due to the monthly sampling. In other words, we're really quite coarse in time. There could be lots of variability for a wide range of reasons over time. And then there's uncertainty because of in-lake processes, like internal loading of phosphorus, total phosphorus moving from sediment back into the water column, for example. These are areas of active research in embayments in the lake, for example. Oh, sorry. Total phosphorus concentrations in the lake in the most recent survey from 2015 to 17 show a decrease in the average lake concentrations, average total phosphorus concentrations. However, select tributaries with mixed land use show consistently high concentrations with total phosphorus loading, cited as important contributing factors of concern for embayments like Canadore Bay. Higher concentrations are also notable on the western side of the lake, consistent with the past 2 surveys that were conducted, and of course to the eastern side in Canadore Bay. For chloride, the lake shows little appreciable change in concentrations from the 2004 survey, and this suggests that any changes to annual loading is small relative to the overall volume of the lake. So increases in loading from the watershed are not large enough right now to challenge or to change overall lake concentrations. So just to summarize, this is the first Lake Nipissing budget of chloride and total phosphorus. And when we, looking at the results of this study, we thought these findings flagged a couple of issues of concern and interest for future management of the lake and its watershed. Impacts of road salt are a potential source of legacy buildup of chloride in groundwater for basins located in cold region climates, and we see that from that's a general statement from the literature. A changing climate and government support for tile drainage could support increasingly favorable conditions for further development of agriculture in the region, so land use. While only modest growth is projected for the region, seasonal, rural, and waterfront properties are an important category of development and land use in our region. For instance, in central Ontario, over decades, seasonal cottages and waterfront properties have evolved into secondary homes used on a year-round basis. So this has implications for land use, for road maintenance, but also for community interest in water quality and watershed management. So we hope that the new elemental budgets presented here provide an opportunity to consider development of a comprehensive watershed scale monitoring program that could extend beyond the limitations of source water protection jurisdictions, for instance, in which the Conservation Authority works. And we could also look at other large regional lakes as potential candidates for envisioning a structure of community-based collaborations. And so I'll leave it there, and I'm happy to answer questions. Thank you for your time and for allowing us to share this work.